All right, hi guys. We're doing 9.5 day 1 today. We're looking at the normal model. So we've looked at different distribution shapes in previous lessons, but we're going to start to focus on the normal distribution. So it says here a data set is said to be normally distributed when its shape is a symmetrical bell curve. And we're referring typically to like a histogram. If you kind of trace the outline of a histogram and it made this nice bell curve, then you can say it's a normally distributed set of data. So the difference here between a normally distributed data set and other ones is typically the middle, the measures of center, are all equal. They're all the same value if you calculate all three, and they're all right in the middle, like the true center of the data. Okay, that's what makes it symmetrical. Another big topic with our normally distributed data sets is this rule of 3 standard deviations, also called the empirical rule, and sometimes called just like the 68, 95, 99.7 rule, and we'll see where these numbers come from in a moment. Basically what it says that almost all data of a normal data set is between 3 standard deviations of the mean. So 3 above the mean and 3 below the mean. You can find most of the data in that range. We've already seen before, if you have a large standard deviation, you'll have a flatter curve. Okay, that's basically what this long sentence says. So the curve might look like this. Well, that's not very good. If you have a small standard deviation, you're going to have a taller curve. So something like this. Both of these are considered normal distributions because they're that nice symmetrical bell shape. The smaller standard deviation pulls all the data closer to the mean versus a larger one, it's more spread out. Okay. The big idea here is this last one. So not only do we say most of the data is within 3 standard deviations, mathematicians have done a lot of research and analysis and studies of normally distributed data, and they've found that it's actually specifically 99.7% of the data is within 3 standard deviations. Okay, so let's look a little more closely at some of these values. So here's a normal curve. Symbols down here, the mu, it looks kind of like a funny looking U. It's just a symbol for the mean. And then sigma, we've seen before, is a symbol for standard deviation. Okay, so there's variables. So in the middle of our normal curve, we would have the mean. And then as we move to the right, we're adding a standard deviation. Here we're adding 2, and then we're adding 3 standard deviations. To the left, we're subtracting standard deviations, subtracting 2 and subtracting 3 from the mean. And we'll do an example of that in a moment. What I really want to get here is the percentages that belong inside each of these little like columns. Okay, so let me give you an example. Like let's say we're looking at height. Height is typically normally distributed. So there's an average height for like men and women, and most people are pretty close to the average. Maybe some are a little bit taller and some are a little bit shorter. And then there's fewer and fewer people that are very far away. So like on the right side here, these would be people that are like 8, 9 feet tall. There's not very many people that tall. Okay, so fewer of the data points would land all the way over here. Okay, so let's look more specifically at how much of the data is in each column. So mathematicians have found that between the first standard deviation above and below, we have 68% of the data. And then between 2 standard deviations, we have 95% of the data. And then between 3 standard deviations, that's where we get that 99.7% of the data. Okay, so we're gonna actually split those up even further because I want to know specifically what's in each column. So if I have 68% between both of these and this is symmetrical, I know that I can divide that by 2, and that gives me 34% in each piece. Okay. Now, if I move one step out, looking at the 95%, well, if I divide that by 2, then I get 47.5% of the data. Now, that would be both of these columns together. On each side is 47.5, but I'm going to subtract what I already calculated. So that means I have 13.5% of the data in this little piece here and here. And then I'll repeat that, 99.7% of the data, split that in half. That would give me 49.85. So these 3 columns together is 49.85. So I'll subtract the ones I already know, 13.5 minus 34 to get 2.35 for this little tiny piece here, 2.35%. This is percentage. And then 2.35 over here as well. Oops, 35. So then lastly, this little piece, well, if the 3 bars on the left are 49.85, and I know this is half of my distribution, that means I have 0.15% left to get to 50% on each side. So we're not going to ask you guys to reproduce like this math over here. This is just showing where these numbers come from. What you need to be able to do is refer back to these values in blue. Those are the ones we're going to use a lot, okay? So let's look at an actual example here and see how we use these values in a real problem. So example 1 says a normal distribution has a mean of 33 and a standard deviation of 4. I'm going to change colors here. Let's see. So we're going to start by labeling our normal curve to model this distribution. The mean, or the average, always goes right in the middle, 33. And then as I move to the right, I'm going to add a standard deviation. So I'm going to add 4, and that would give me a value of 37. If I move to the right again, I add 4 again, 41, and then lastly is 45. So this is like plus 3 standard deviations above the mean. Same thing as I move to the left, but this time I'm going to subtract 4 because I'm moving to the left. So here's a value of 29, here's a value of 25, and here's a value of 21. Okay. Now, this is good, but what you really need are those percentages we just talked about. So I'm just going to copy those down exactly. So I have 34 and 34. These are percentages. 13.5, 2.35, and then the little baby one is 0.15. Same thing over here. Having them written down makes it really easy when we do some calculations here in a moment, so you don't have to try to remember the value of each thing. You can just see it right there. So let's look at some problems now that we've labeled our normal curve. We're looking for the probability that if we just picked a random piece of data from this set, we're looking for the probability that random piece is in a given interval. Okay, so for example, what's the probability that if I just picked a piece of data from this data set that it is more than 37? Well, I go to my normal curve, I find 37, so here's my 37. Values that are more than 37, meaning the ones in red, those are going to be to the right. So I'm going to add up the percentages that are to the right of 37. So 13.5% plus 2.35% plus 0.15%. Okay, I'm adding the percentages, not the values at the bottom. When I add up those percentages, I get 16%. Now, when we're talking probability, that means we want it to be a decimal, not a percent answer. So instead of leaving as 16%, I'm going to move that decimal 2 to the left, so it's 0.16 for my probability. Okay, not a huge deal. Sometimes we ask for percentages, sometimes we ask for probability. So what that means is there's a 16% chance that if I just grabbed a number out of a hat from this data set, that it's going to be bigger than 37. Okay, let's go down. I'm going to skip down to C. So between 29 and 37, well, that's pretty much like it sounds. I find 29. I'm going to change color here. Here's 29. Here's what 37 is. Between them would be these two rows, or columns, I should say. So let's add those percentages. 34% plus 34% gives me a total of 68%. As a decimal, meaning a probability, it's just 0.68 with no percentage sign. Okay, I'm going to do 2 more with you, and then I'll have you try the other column on your own. So at least 25 means that 25 is the smallest value, right? At least 25. It can be anything bigger, but at least 25. So I'm going to find 25 on my normal curve. This is the smallest. This is at least. That means I can add up everything to the right. Okay, so I'm going to add up all the percentages to the right. 13.5 plus 34 plus 34 plus 13.5 plus 2.35 plus 0.15. That's everything to the right of 25. 97.5%. But as a decimal, it'd be 0.975, meaning the probability is 0.975 that you pick a value and it's at least 25. And then last one together here, at most 37 means that's the highest number possible. So I'm going to find 37. Here's my 37. I'm going to show up here. 37 at most, meaning that's the biggest one. So I'm actually looking at everything to the left this time. So I'll add up all the percentages to the left of 37. When I add those up, I get 84%. As a decimal, it's 0.84. Okay? So what I want you to do is to try the 4 problems on the right side on your own, and then you'll be able to pause the video and check. All right, here's my answers for the first 2, and then I'll scroll down so you guys can see the last 2 in a moment. For less than 33, that's right in the middle. 33 is our average. So if I'm looking at anything less, that's actually half, exactly half of the curve. So I didn't have to add those up. You could totally add all the values up and you should still get 50%. Either way works. And then between 33 and 45, I got 49.85%. As a probability, it's just 0.4985. Okay, and then try the last 2 down here. All right, here are my answers for the last 2 problems. For F, I got a probability of 0.84, and H at most 21. That's the very, very teeniest piece of our normal curve, so it's 0.15%, nothing to add together there. Converting that to a decimal, move the decimal 2 to the left, I got 0.0015 for the probability.